following video is for section 6.2, integration by substitution. On day one, we're going to look at integration by substitution in some of its more basic forms. Integration by substitution is when you take the antiderivative, or you're integrating, and you have a function that if you look at what's happening, the chain rule would essentially be in effect. So we're basically undoing the chain rule when we anti-differentiate. So anti-differentiating is undoing differentiation. When we have to do substitution, we undo the chain rule. Typically, we use the variable u, so this often has the name u substitution. So you will often hear u substitution as the vocabulary that a teacher might say in class, or you might see it on the internet as u substitution. So let's look at problem one. We would make u equal to x plus 1. Now, what's the benefit of that? So we can now integrate u cubed. So now we don't have x plus 1 in there. Now it's just something that's really nice to integrate, u cubed. But notice we had a dx. We also have to change that to be du. So if I have u equals x plus 1, if I take the derivative of u and x and stuff, I have du equals dx. So I take the derivative of both of these parts. Basically, I basically take differentials on both u and x. I have du equals dx, and then the derivative of 1 is 0. So du equals dx. So in this case, I can replace dx with du. So I have u cubed du. Now I take the integral of this, I get 1/4 u to the 4th plus c when I anti-differentiate with an indefinite integral. So 1/4 u to the 4th plus c. And then the last step is taking whatever u was and replacing it back in again. So 1/4 x plus 1 to the 4th plus c is our final answer. Notice if I took the derivative of this, I would do 4 times 1/4 x plus 1, and then this number would go down. So I would end up with this again. Now I said there would be a chain rule. Now technically you would have to, if you're taking the derivative of what I just put an arrow next to, you would have to take the derivative of x squared, or x plus 1. It's just the derivative of that is 1, so it doesn't really show up looking like the chain rule. But as we move on, it will become more obvious. So in problem 2, a good choice for u would be 2x minus 5. So I'm going to integrate u to the 4th. Now I have to make a substitution for dx too. So du equals 2 dx. Notice that the derivative of negative 5 is 0. So in this case, we have du equals 2 dx. I need to get rid of dx in here and replace it with a du. So if I solve for dx, I divide by 2 on both sides. I get du over 2, or 1/2 du. So I can replace dx with 1/2 du. Now 1/2 is a constant. I can rewrite that on the outside of the integral. So then I can integrate u to the 4th. I get 1/5 u to the 5th plus c. So my final answer in this case is going to be 1/10 times 2x minus 5 to the 5th plus c. Sorry, I have some of this blue stuff over here, so let's move that out of the way. 1/10 2x minus 5 to the 5th plus c. Notice if I took the derivative of this, the c would go away, and then I would have 5 times 1/10 2x minus 5 to the 4th. Notice 5 times 1/10 is 1/2. And then remember that I have to do the chain rule, so times 2. So all of this stuff would go away. So all of those constants would end up going away, and we'd get what we started with back. So that's good. That's basically what's happening. I just want to keep reminding us that what is essentially happening is we are undoing the chain rule. Let's take a look at problem 3. So uh, problem 3 is the integral of 2 natural log of x over x dx. So I basically have two different things that are happening. I have a natural log of x and an x, and I have to choose which thing is going to be better as u. If I make x equal u, that's useless. That doesn't really do anything. That wasn't meant to be a pun, useless, sorry. But there's no x, that doesn't do anything. It just replaces all the x's with u's and we're still in the same situation. But if I make natural log of x equal to u, du equals 1 over x times dx. So notice what happens. If I make natural log of x equal to u, I now have 2u. And then notice that dx, which I have to replace, is x times du. So remember, I had this x in the denominator originally. I'm now going to multiply this by x du, because that's what replaced dx. And notice that these x's are going to end up canceling. I'm not allowed to ever take an integral if I originally had x's in there and I replace things with u's. I'm never allowed to take the integral if I still have u's and x's mixed together. So notice originally there were all x's. Down here there have to be all u's or else I can't do anything. So notice that when I made my u substitution, that x conveniently canceled out. So that's something to always look for, and we'll find it a little bit later in certain problems, number 5 and some later on. Look for things that can conveniently cancel out when you replace this dx with du. So in this case, the x conveniently cancels out. So I have the integral of 2u du, which is u squared plus c. And then I'm going to replace u with natural log of x because that's what it was. So it's the natural log of x squared plus c. It's my final answer for number 3. Number 4, we probably can tell that the answer is going to be 1/7 e to the 7x plus c, because if I take the derivative of this, I end up with 7 times 1/7 e to the 7x, which ends up just being e to the 7x. But I'll show you what u would be just to do it kind of quick. So if I make u equal to 7x, du equals 7 dx. So if I replaced dx, notice that du over 7 equals dx. So I take that, I replace dx, and 7x replaces u. So if I had the integral of e to the u times 1 over 7 du, I would have this 1/7 on the outside. And of course, the integral of e to the u is e to the u. So it ends up being 1/7 e to the u, which then I replace the u with 7x. Number 5, in this case, I'm going to try u equals 2 minus x squared. So du, the derivative of 2 is 0. This ends up being du equals negative 2x dx. Now notice that there was an x in the numerator. When I replace dx, I'm going to replace it with negative du over 2x. So what's going to happen is when I replace dx with du, I get a negative sign thrown in. I get a 2 in the denominator thrown in. But this x that was in the numerator is going to cancel out with an x in the denominator. So let's rewrite this. I'm replacing 2 minus x squared with u. I have a du in the numerator. I have a negative 1/2 that's going to be in there now because I have this 2 that originally wasn't in the problem and this negative sign that originally wasn't in the problem. And then I also have the x that was up here originally is canceling out with an x that's now in the denominator. So both of those things go away. So now I have du over u, the integral of that. I can also write that as negative 1/2 the integral of 1 over u du, if that helps you visually. Notice that the integral of 1 over u is going to be the natural log of u. So I have negative 1/2 natural log, the absolute value of u plus c. And when I replace u with 2 minus x squared, I get negative 1/2 natural log the absolute value of 2 minus x squared plus c. Number 6, in this case, u will probably equal 2x plus 3. Du is going to be 2 dx, which means the dx is 1/2 times du. So I'm going to replace dx with du, but there's a 1/2 that goes in there with it. And then u replaces 2x plus 3, so I get 1 over u times du. So the integral of 1 over u is natural log of the absolute value of u plus c. And of course, there was a 1/2. I'm going to replace u with 2x plus 3, so I have 1/2 natural log absolute value of 2x plus 3 plus c. One thing to notice, and I haven't really hit it in a little bit, but I'm going to talk about it again. If I take a look at all of the things that I'm circling right now, I can always check whether I did it right, because if I take the derivative of my answer, I should end up with whatever was originally inside of the integral. So if I take the derivative of these things and it doesn't work, then it doesn't get what I started with back, then I didn't do it right. So that's one way that you can check whether all these things are right or not. Number 7, if we take a look at number 7, we have x cubed plus 2 on the inside of a square root and x squared on the outside. Notice that that x squared is kind of in the way, but good news is if I make u equal to x cubed plus 2, when I take the derivative, I'm going to get an x squared. So then that's going to cancel the x squared that's originally in there out. So that's something that you want to look for when you're choosing your u. If there's something that's kind of floating around, you want to find a u that when you take the derivative and get du, it's going to cancel the stuff out. So my two choices for u in this case could be the square root of x cubed plus 2. That's a bad choice because if I take du there, I get 1/2 x cubed plus 2 to the negative 1/2 times 3x squared. The x squared is going to cancel out with the other x squared, but then when I replace this whole thing with u, then I'm still going to have like the square root of x cubed plus 2 in the denominator, and so then I have like a u. It just becomes not very convenient. So instead, what I'm going to do is I'm going to make u equal to x cubed plus 2. And again, what I just did, it's not the worst thing in the world. It would end up being okay, probably, but it just makes it a lot more complicated. Whereas here, if I choose u to be x cubed plus 2, I get 3x squared as du. And so that, or I'm sorry, dx. So that's equal to du. Then I divide, so I get 1 over 3x squared du equals dx. So now I can make all my replacements. So this x squared ends up canceling out with the 1 over 3x squared, and I just have a 1 over 3 that's left over from this substitution for dx into du. Now I integrate, the x squared's canceling out, the square root of x cubed plus 2, I'm making a u substitution, so that becomes the square root of u. I'm going to write it as u to the 1/2 to make it a little bit easier. And then I do du. Now I'm going to integrate this, so I have a 1/3. The integral of u to the 1/2 du is 2/3 u to the 3/2 plus c. So now I combine the 1/3 and the 2/3, and I replace u, and I get my final answer. So I have 2/9 times x cubed plus 2 to the 3/2 plus c. Number 8, I'm going to do this one relatively quickly. U equals 3x, du equals 3 dx. So that means when I sub in dx equals du over 3. So I'm going to have the integral of sine of u du, and then I have a 1/3 constant on the outside. The integral of sine is negative cosine, so I get negative 1/3 cosine of 3x plus c. Now, if I look at a problem like number 8, as I get better with U substitution, I can probably do that problem without actually formally writing U equals 3x. I can probably do that one in my head. Same thing with a problem like number 1, possibly number 2. That might be something that you can do in your head. But for a lot of people, problems like 3, 5, 6, actually 6 you can probably, some of you might be able to do in your head. Problem like 4 you might be able to do in your head. But a problem like 5, problem like 7, problem like 9 or 10, a lot of times you're going to have to actually write that out. Um, Unless number 9 you memorize. Speaking of number 9, let's talk about that. Tangent of x dx. We don't know the integral of tangent, at least not yet. So when we take the integral of tangent, if I make u equal to tangent x, this is not going to work because du equals secant squared x dx. So if I replaced this, I would have u divided by secant squared x times du. And clearly there's a u and an x in there. That won't work. So I need to make a better choice. And when I'm looking at this, notice that tangent is the same thing as sine of x over cosine of x. So if I take a look at what I have two choices. I can either make u equal to sine or u equal to cosine. If I make u equal to sine, du equals cosine x dx, which means that I have the integral of u du over cosine x, and then there's another cosine x that's going to be put in the denominator. Again, I still have an x and a u in the same problem. So this is, again, a poor choice. So the reason why I'm going over some of these is sometimes you might make a poor choice and you have to realize that you can't do that. You have to try something different. So in this problem, a good choice for you would be cosine of x, because then du is negative sine of x dx. And then what's going to end up happening is when I integrate this, I replace cosine x with u, and then there's a sign in the numerator that when I replace dx with du, the sign is also going to end up being in the denominator, so those are going to cancel. So I had a sine x in the numerator, there's going to be a sine x replaced in the denominator, those end up canceling. So I end up with negative 1 over u du, or negative du over u. Um, so the integral of negative 1 over u du ends up being the negative natural log of absolute value of cosine x plus c. So notice that u is cosine in this case. There's a lot of stuff going on. I'm going to choose the actual correct thing to make u. If I make u equal to tangent of 2x plus 7, notice that du is 2 secant squared 2x dx. And what ends up happening here is I perfectly am going to get rid of the secant squared when I replace dx with du divided by 2, or 2 secant squared of 2x. So let's integrate this. And I end up with the integral. It's going to be 1/2. And then if the secant squared 2x was in there originally, I'm going to replace tangent of 2x with u. And then when I replace dx with du, I also have a secant squared 2x that goes along with it when I substitute in the du. And remember, the 1/2 went in with it also. So I have 1/2 times the integral of u du, which means the integral of u du is 1/2 u squared. So this becomes 1/2 times 1/2, which is 1/4 u squared plus c. And then I'm going to replace u with tangent of 2x plus 7. So I get 1/4 tangent of 2x plus 7 squared plus c.